Hi friends, welcome on board for another project. This is an ultrasonic range finder circuit. Here is the hardware, the circuit board. It is powered using this USB Type-C cable. And here is the display, a graphical user interface of course. This number shows the distance between the sensor and the object, and this circular progress bar is to visually show the distance between the minimum and maximum detectable range. The maximum detectable range is 300 centimeters. So 171 should be somehow in the middle, a little bit higher, okay? Because the middle point is here. These two numbers define the threshold for the buzzer and relay activation. So 30 for the buzzer means if the distance is below 30, buzzer is fully active. Before that, the buzzer will signal. I will show you. And this 40 means if the distance is below 40, the relay, this one is active. And the relay might be connected to whatever AC or DC load. You can modify all of these parameters. Even this one, you can turn on and off the buzzer. You can move between the elements or the widgets using this push button. You can see the focus rectangle. It is similar to the tab key of the computer keyboard. For example, I enable and disable the sound and move to this buzzer and increase it or decrease it. Okay? And as simple as this. Really, programming this board was not easy, especially this LVGL libraries and these coding. So let me show you how it works. At the moment, 171 is the distance. Let me put my hand in front of the sensor. So come down. So the buzzer gives some signal. But if we go below, so below 4D, the relay is active. Do you see the red LED? And below 30, the buzzer is fully active. It works as nice as this. So to explain the hardware and the board, I should disassemble everything and show you the circuit and the components. So let me pause the video at the moment. Alright, I disassembled the connected hardware. Let's start from the main board itself. So here is the PCB board. As usual, I designed the schematic and PCB for this board also using Altium Designer, and I have uploaded the design files in my personal Altium 365 cloud space. So simply follow this link in my YouTube video description and sign up on the Altium 365 website for free. Then follow this link and download the design files. Let me start from the power input. This is a USB Type-C connector. It means you can power this board using your mobile charger, for example, or any other 5 volts power source. Here is the input filtering stage, an RC filter, then this 3.3 volts regulator to power the microcontroller board and the display here. This is a 5 volts Panasonic relay. It gets the power from the 5 volts input. It means this relay will not cause instability for the rest of the circuit. Here is the 4 pins XH connector to connect the ultrasonic sensor, and these two MOSFETs provide or to translate 5 volts logic to 3.3 volts logic for the microcontroller, because the ultrasonic sensors come in a variety of shapes and designs. Some of them support 5 and some of them support 3.3 and 5. So for this board, doesn't matter, you can use whatever ultrasonic sensor. This connector is for the buzzer. This is a 40-pin FPC connector, and your most challenging point in soldering is to solder this FPC connector. And I highly recommend you to use a microscope to solder this connector because it is pretty easy to build solder joints on these tiny pins. Here is the microcontroller board, RP2040 from Waveshare. This is a very nice and tiny board because the microcontroller is pretty powerful, dual core, 200 MHz without overclocking, and 2 MB of flash memory. Pretty suitable for applications that need graphical user interface because I mostly use LVGL to build a graphical user interface. And flash memory is critical for such applications. Let's go to the bottom side. Yes. So the bottom side, here is the ground. To reduce the length and impedance of the ground path, the result is lower noise and higher stability for the circuit. This capacitor is to dampen the possible relay noises, although I have protected this MOSFET, this switching MOSFET, using this diode. This capacitor is something extra. I have prepared this clearance between the PCB and this output because my assumption was that you might connect some AC or high voltage DC load to this terminal. So this clearance is pretty mandatory. I think I covered all of the points. If you have questions regarding this board, leave me your question in the comments, although I will explain even more in the schematic and PCB section. Here is the ultrasonic sensor. It is connected to this connector, so these two 4-pins connector. As I said, you can find a variety of sensors or modules on the market. And because this board is this board provides 5 volts, you can use whatever module you like. This comes with a pin header, so I have desoldered the pin header and soldered this XH connector for easy connection. The back side goes to the single ultrasonic sensor, this one. Let's go to the LCD. Here is the LCD. So this is a 3.2 inch LCD, 320 by 240 in pixels. This is a flat extension. You can directly connect the flat cable to the board, but for easy demonstration I use this extension and connect this white flat cable to the board. Otherwise, as I said, you can directly connect the LCD cable, flat cable, to the board. You are not bounded to use this extension. The LCD doesn't have some kind of touch because the screen is small. The touch is not feasible for such a display, so I use 2 push buttons to navigate between the graphical user interface elements. And lastly, this is the buzzer. I put this on the buzzer because the sound was strong for my small room. Otherwise, dependent on your application, you can put this or remove this sticky. This XH connector goes to the 2 pins XH connector of the board. I covered everything, isn't it? So if you have any questions, just let me know in the comment section. I explain in more details in the next section because I open the schematic and PCB. Alright, here is the home page of my Altium 365 cloud space. I have uploaded all of my projects here so far. These 12 projects I mean, and the rest belong to the Altium itself. You can use them as a sample. You can create your own space as well, and it's free. Just follow this link in my YouTube video description and sign up on the Altium 365 website. You might even get some nice offers. Then open your space, upload your PCB projects, and share them with your friends or teammates. But you may ask, why? What's the catch? Altium 365 has many features, but one stands out. It makes teamwork easy, especially for complex PCB projects. Imagine a team where one person works on the power supply, another designs the digital circuits, and someone else handles the RF parts, such as Wi-Fi and Bluetooth. Another team member creates the bill of materials and buys the components. If you use the traditional method, I mean the email, to exchange project files and comments, things will get messy. It leads to lots of attachments, misunderstandings, errors, and frustration. This will delay your project, stress the team members, and affect the company's income and reputation, of course. But with Altium 365, the whole team works on a secure cloud platform. Everyone can leave comments, suggest edits, update component values, and more, all in one place. If you have worked on a complex PCB project, I'm sure now you feel the difference. So I won't explain more, just follow the link and try it yourself. Here is the latest project, by the way. When I double click, the project documents open right away. Here is the schematic document. This one is the PCB layout, and this one is a 3D view of the PCB board. Let me start to explain the schematic from the power input or USB connector. These two pull-down resistors are to indicate that this USB Type-C is on the load side. However, because the current consumption of the circuit is low, we can leave these two resistors and don't solder them. If you have noticed, I had not soldered these two resistors on my board also. The input voltage 5 volts goes through this low-pass RC filter for noise reduction, and then this regulator stabilizes the voltage on 3.3 volts because we should supply the RP2040-Zero board and this TFT display only using 3.3 volts supply. Look at here. When I put the cursor on the net, the platform highlights the net on all parts of the circuit. This feature is very helpful when you want to demonstrate and discuss the schematic to your colleagues and teammates on a big 4K or HD TV. Let's go to the TFT. I have configured the TFT display for the SPI data using these three resistors. Actually, these three resistors are setting. So when I use the SPI, I have to pull down or connect all of the data pins to ground for noise immunity. These two capacitors are decoupling. Let's go to the RP2040, the same as the TFT. These two capacitors are decoupling, and this Schottky diode allows us to debug the RP2040 board and also connect the power, because the 5 volts from the power and 5 volts from the USB debugger should not conflict, and this Schottky diode prevents this. This blinking LED blue, if you remember from the previous step, is this one. Here is the relay. This MOSFET is to switch the relay, and this diode is to protect the MOSFET. This LED is to indicate that the relay is on or off, and as I said in the previous step, this capacitor is to dampen any possible noise of the relay. This is apart from this protection diode or auxiliary diode. Some people call this auxiliary diode. These two push buttons, I have pulled up the pin so the microcontroller detects the ground or zero voltage. I prefer this one. And these two MOSFETs are configured to translate the 5 volts logic to 3.3. This is the cheapest method and works pretty well for this circuit. You can also use some chips, but it's not necessary. When this works, why you should use some conversion chips. This X-edge connector is to connect your ultrasonic range finder sensor or module. These two capacitors are decoupling for the module, and this MOSFET is to turn on and off the buzzer, the 5 volts buzzer. I explained everything, yes. So let's go to the PCB. So this is a 2 layers PCB board. If I disable the top, so the blue is the bottom layer, and most of the tracks is on the top, because my plan was to use the bottom layer as the ground as much as possible. However, we have to use some tracks on the bottom also, because 2 layers is not similar to 4. In most of the circuit, we have to pass some tracks from the bottom, by the way. So if I disable the top overlay, you see, now it's easier to demonstrate. There we go. This is the bottom layer. And as I said, such method will reduce the length and impedance of the ground path. The result is less noise or lower noise and higher stability for the circuit. These vias or wires, I have placed these wires for the same purpose, near the critical components, near the ground pin of the capacitors, decoupling capacitors, near the ground pin of the TFT display, and whatever place I feel it's necessary. One nice feature of this Altium 365, look at here. If I double click on the track, you see it highlights all of the parts of that track, and this track or net is the input supply. As I said in the previous step, the relay is directly connected to the input supply from the USB. Let me show you the 3.3 volts. You might like to see. You see, this is the path for the 3.3 volts supply rail. It goes to the microcontroller or the RP2040-Zero board and the TFT display. This feature is also very nice for demonstration. As I said, on the big 4K or HD TV, these features are very nice. These SPI pins, let me show you. It is true that the speed of the SPI connection is almost, I can say so or high. It's around 32 megahertz, but because the distance from the TFT and the microcontroller is low, we can leave this as it is, and we are not bounded to use differential or length matching method for this SPI clock and data. You know what I mean? The clock frequency is not that much high, and the length for the SPI, the SPI connection, is short. So this works very well, and you see the circuit also works very well and stable. I have placed the decoupling very close to the components. This technique is also very important. This decoupling and the decoupling of the RP2040 on the back side, decoupling near the regulator, and as I said, this clearance near the relay or this terminal, because you might connect a high voltage AC or DC load to this terminal. I think I covered everything. If you have any question, just leave just ask your question in the comments and leave comments. I hope you like this video. Don't forget to share and subscribe. We will do something else in the next video.